Okay, I've started the recording of the session, and once again I welcome you all. The the class is CPE. Can you see my screen, please? Just show your reaction. Okay. Can you see my slide? Let me see your reaction. Thank you so much. Oluwaseyi, thank you, thank you. Okay, so um, this lecture is dedicated. I mean, it's 31301, continuation of where we left from yesterday. We're moving on to chapter 2, and in chapter 2, the following will be considered. So the overview is as follows. We look at general concepts. Chapter 2 is uh, dedicated to the processor architecture, that is x86 processor architecture. As I said previously, that a good understanding of the architecture of the processor, whose assembly language is to be considered, is very, very paramount. It's unlike high-level programming, wherein the architecture of the processor is hidden from the programmer. In assembly language or low-level programming, the architecture is very, very paramount. A deep understanding of it is important. And so this chapter is dedicated to that. And as much as possible, I will take you through the chapter. Uh, so we look at general concepts of the x86. We're going to delve into the instruction architecture 32, the processor architecture. Then we'll also look at the memory management, because as in programming deals extensively with memory activity as much as processor. Then we'll look at 64-bit processor. A typical 64-bit processor is a Pentium. Diamond Ibituyi, please mute your microphone. Okay. And then we'll move on to the component of an instruction architecture 32 microcomputer. Then we'll end up with the input output systems. All right. Okay, so general concept of a processor simply, or a computer system, we're going to look at the basic microcomputer design. We're going to consider its instruction cycle or instruction execution cycle. Please pay attention to that. We're going to also look at how information is read from the memory and how program is run. So these are the concepts that has been considered as general concept. So let's look at the a basic microcomputer design. A typical microcomputer design is depicted as follows. if you see my screen, a typical microcomputer, which is implemented as a laptop, what we have at laptop now, desktop, is depicted as follows. It must have a central processing system. Within the central processing system are the following component: registers. Registers are storage facilities for storing data. It must provide for a unit known as arithmetic logic unit. That session simply performs arithmetic operations and logical operations. What are arithmetic operations? Addition, subtraction, multiplication. What are considered as logical operations? Comparison, greater than, less than, equal to. Then again is the control unit, described as CU. Control unit provides the interpretation to the various activities the CPU or the various functions the arithmetic logic unit can perform. If you remember yesterday in class, I mentioned instruction set. I said instruction set is the set of instruction a CPU is able to execute, and the component, the unit within the CPU that is represent that does that is the control unit. So the instruction architecture or the instruction set are domiciled in the control unit. Now, there is the section described as clock. For every digital system, there is a clock or a clocking device. What does a clocking device, what does it do? It ensures the synchronization of activities. Usually, I describe a microcomputer, the processor within a microcomputer, as similar to a human being that has um, challenge with his or her sight, that is physically challenged, who is not able to see or who is not able to use his vision sensory, but is able to move around, is able to feel, is able to touch, is able to listen to instruction, but does not have the services of his doesn't have the service of his visual sensors or sensory organ. Okay, I've been rightly told that there are some students who could not join, so I'm going to halt the lecture for now to bring in others. The recording, that's fine. So I was explaining that the basic microcomputer um, comes up with this design. It must have a central processing unit made up of four components: registers, store meant for storing of data, ALU for computing, for performing arithmetic and logic operations, control unit for storing instruction sets, and clock for synchronizing activities. As I mentioned, that the processor of a computer, of a computing device, can be likened to an individual who is challenged visually, is unable to see, but has well-developed sensory, other organs are well-developed: touch, taste, feel, and all of those. Then attached next to the central processing unit is the memory or the storage unit for storing instruction and data. Please note that there's a difference between instruction and data. I give a typical example. In Python, print A, B, C. Print A, B, C is the instruction, and it has the command and the data or the operands. The Data or the operands are stored separately. The instructions are also stored separately. Next to the memory or storage units are the input-output devices that is provisioned for uh, devices that are able to connect data or the user to the processor or connect the processor to the user, and there can be as many as possible. Now, if you look at the interconnectivity, the CPU is connected to the processor, sorry, the memory, the input output devices are along three paths. The three parts are very, very key. You must please note these three parts. The three parts are the pathways of instructions and data. The first pathway is the data pathway, which can also be described as the data bus. That infrastructure conveys data. As I mentioned to you, print A, comma B, comma C, data will A, B, C are the data. Print is the command. The instruction is made up of the command and the data. The data will move along a different path. And then the instruction, which is control, will also move along a different path. So control or the operations to be performed on the data will be transferred on the control lines or control bus. The address bus will describe which of the locations, which of the resource or resources is being addressed. For example, if addition is to be performed on A, let's say add A to B and store in C. So the operation is addition. Add A to B. Add A to B. So addition will be obtained from the control unit and then will be sent to the arithmetic logic unit for interpretation. And then the data to be executed will be made available via the data bus. So you can see that the three infrastructure play major role, and they all operate at the same they all operate synchronously because the what's it called um, the clocking system, the clock is able to synchronize. The clock instructs when an action should be taken and when an activity shouldn't be taken. I see that some students wants to join. Let me try and admit them. Their request, okay. Let I'm trying to admit. Okay, that's Adedeji, please mute yourself.
Okay, sir.
Okay. I think I've been able to bring in as many as possible. So, as I said, the three buses, data, control, and address, are very, very key. And the clock is able to synchronize all of this at the appropriate time. So timing plays a major role in uh, the activity of the microcomputer. A number of students are joining at various times, so distracting this class. Okay, next slide. Now, I have just mentioned to you clock. What the clock simply does is that the clock generates pulses. These pulses are timing signals that determines when activities or actions should take place. Please mute yourself. Okay, so if you take a look at a typical clock train, it's a voltage level, pulses from 0, and then it rises to 1 and goes down. So one clock cycle is from one rise to another rise. So this is a clock cycle. So what happens here is that the computer is able to trigger events based on the various timing on the clock. So it can say, for example, let the data be read at a at this point, and then let at maybe at another time on the clock pulse, let the address be read, and then other activities take place. So the activities of the CPU and the bus operation are synchronized based on the um, clock train that is generated. Clocking is very key. Again, now let's move on to instruction set 32 processor architecture. So let's look at the 32-bit processor architecture. So in a typical instruction set 32 processor, we are interested in the cycle of instruction execution. What do I mean by that? What is a cycle? How does how is a typical instruction executed from start to end? And here's a simple example of five, a typical example of 5 stages through which instruction execution runs through. An instruction must be fetched. Remember that I told you that an instruction is made up of a command and a set of operands. You want to ask me, must every instruction contain operand? Operands are data. No, but every instruction must contain a command, at least. So in x86 processor, the maximum number of operands an instruction can bear is 2. and the minimum is 0. So an instruction must be fetched from the memory. When it is fetched from the memory on the at the instance of the clocking of the clock. Let me take it back again. So I want you to look at the clock here. It's a very major component of a processor, and it generates trains like this. So an instruction is fetched from the memory. Remember, this is the memory. It's fetched from here into the CPU. And when it is fetched, it is decoded. What does decode mean? That is the operation part or the control part is extracted and interpreted. So when the control part is extracted, it is brought into the control unit for interpretation. That's what is described as decode. When it is decoded, the next thing is to fetch the operand. For example, A equals B plus C. B plus C are two operands. A is another operand. A holds the result of the addition of operands B and C. But the instruction is that B should be added to C, and the result of the addition be stored in A. So there are two operations, addition and storage. So decode interprets and then identifies the circuits that should perform that. Remember yesterday class I told you in the when I was describing the virtual machine, I said the lowest level is the digital logic. So once the code the CU contains the instruction set, but the decode interprets the instruction set and also identify the digital circuit that should implement the operations. Once that is done, the next level of activity is to fetch from memory here, the data or the operands. In the case of A equals B plus C, it's going to fetch B, fetch C, what should be in A, in B and C, hoping to sum the two and then place the results in A. So the next stage is what? Execute. So at the stage of execute, remember that the control has been decoded, the circuits have been identified, and the data has been fetched to, that's operand, placed in the arithmetic logic unit. So the next thing is to execute. The execution will be in sequence. First is to add B to C and then transfer the result to the to transfer the result to A, which will be implemented as during the store cycle, the store stage rather. So this is a typical instruction cycle phase. It starts with fetch, decode, fetch operand, execute the instruction, the operation that has been decoded with the aid of the operators or the operands, and then store the results in the memory. Immediately that is done, it goes back to fetch. And that's why execution in every programming language is sequential. Every line of code must pass through fetch, decode, fetch operand, execute, and store. Once store is done, then it goes to fetch. If you then want to ask me, what does it fetch next? It fetches the next instruction. So let's assume you have a program snippet, 10 lines. Once first line is fetched, the line 1 is decoded, is the operands are fetched, the instruction is executed, then the results are written in the memory. The next thing is to fetch the next instruction. It continues until it encounters stop and end. So this is what is known as instruction execution. And that's all that is in this diagram here. You can see the memory contains code and data. Code and data. For example, when you write your program, you put data somewhere and then you put your code somewhere. So both are read. Data will be streamed along the data bus. Code will be streamed along the address and control. And then the stages of instruction of execution will then take place. For example, both data and address are fetched into a code cache. Thank you, Adesina. Thank you. Code cache. That's thank you, Samuel. Thank you for the reaction. So in the cache is another version of memory. It's a specialized version that is designed for speed. And then so what happened here is that the instruction is fetched into the cache, and then the cache then passes to an instruction decoder. Remember, in the instruction decoder, what it simply does is that it splits the instruction into two parts, into operand and command. The command part goes into the control unit. But can you see this arrow that goes back? The instruction pointer. What that does is that at that stage, it tries to locate the next instruction, which is your next line. But know fully well that the instruction number one has not been fully executed, but it's on its way. So afterwards, what happened is that the control unit takes over, tries to interpret the command. In the case of the example I gave, add, and then it's then select the arithmetic logic unit. From the arithmetic logic unit, select the appropriate digital circuit to perform addition. Now, the operand is assumed to have been positioned within the registers. They have been read from memory and then streamed into the registers so that the arithmetic logic unit can perform addition. The result is also sent into a register in preparation for the data to be written in the memory. So there's also a data cache. A data cache is a specialized memory that holds on the outcome of the operation, which is writing it into memory. And then from there, it then takes it into the memory. Now, you can see that for every operation in the code cache as well as the data cache contains both data and address. The reason is this, so that wherever the data is to be written must be identified. Must be identified. So the address, for example, when I say A equals B plus C, where the data is to be read from are B and C, which are specialized location in the memory. So the address data, the address bus rather, convey such information. Then the data to be read or to be read into are obtained from those addresses and then put on the bus. Like so now, if you then ask me, how does the processor synchronize all of this? What do I mean by synchronization? How does the processor ensure that what is to the activity to be where the activity to be performed at the right time is performed, and then what activity to take place afterwards is brought in at the right time? That is where the clock comes in. The clock takes that role. And the function of the clock, as I said, is to synchronize. The speed at which the clock is able to synchronize is a function of the speed of the compute of the processor. That's why you can have a computer that is 1.7 gigahertz and another that's rated 2.2 gigahertz, meaning that the clock train are not the same. That a processor is able to generate so many clock trains, 1.7 billion clocks in 1 second, and while the other is able to generate 2.2 billion clocks in 1 second. Okay, I'm trying to admit someone. I can't find this person again. Okay, maybe he's gone. Okay, that's fine. All right. So that's about the instruction cycle. Does anybody have any question? You can raise your electronic hand if you have a question. Okay, none. Okay, that's good. So let's move on. Okay, so I've just described all of this. So you can read the notes, read the text. We have described the process of reading from memory, from cache. Now, the next thing is, how does a program run? How do you run a program? Let's look at how a program is run. A program emanates from a user sent in as a file with a name onto the operating system. The operating system searches for the program in a directory. Once it is located, the um, the program loads through the operating system into the memory, and then it begins to run. When it gets to the end, it terminates. Return control to the operating system. Any question? No question, Tafik. Thank you. Okay. Now, we want to look at the various modes of operation within a processor, an x86 processor. There are, when we say mode, the processor can operate in 4 different modes. The first one is protected mode. This mode is native to Windows and Linux. There is another mode known as real mode. Real mode. In the real mode, in a real mode, the mode that mode as real mode is native to MS-DOS, which is the traditional operating system mode created by Microsoft right from the onset. Very, very limited. It does not support graphics, but and it has a lot of challenges. But that has been upgraded. The weakness obtained or observed in MS-DOS was improved upon to develop in real mode was developed to produce protected mode. In real mode, what that simply means is that it can only recognize 10 segments. A segment is 64 kilobytes. 2 raised to power 16 can only recognize 16 bits of location and maximum of 10. That gives 640 kilobytes. I'm proud to tell you that when I started computing in 1991, the first set of computers I used were 640 kilobytes of memory. Very, very tiny. Um, we could hardly do graphics. We could hardly do graphics. And much later, that uh, programming environment was improved upon to produce what is called protected mode. In protected mode, what happened is the operating system is able to partition the memory into different memory segments. These segments can operate independent from each other, and that's what gave the name protected. These locations are protected from the other memory location. Let me tell you some of our experience in those days. You may be operating on your computer and suddenly the computer freezes. We describe such situation as the computer is hung. What has happened is that is either the program that you are running has eaten up the memory, or is trying to the memory is trying to um, interfere, or is trying to cross into another section that it shouldn't be. So we had a lot of issues with memory management. But when protected mode came, each program is able to operate within a protected area of the memory. And another a third mode of operation is known as the system management mode. And what happens at that level is power management, system security, and diagnostics operate. For example, your BIOS and all of those. That's the level upon which the system, the processor can operate. Now there is
That time they went to big other like
I
this.
did to meet your mic.
Because when one take, I was having it.
I did to
No, she be activate. But that's for me, like that. Me like it. You my mom.
all right. Ogechi, you cannot hear me. Check your network. You should be able to hear me. Okay, so now the fourth kind of um, mode is referred to as the virtual 86 mode, which is a hybrid of protected mode in which each program has its own 8086 computer. That's highly um, sophisticated, and which is what is further developed to what we have as of now. Okay, so now let's look at the basic environment of the processor. We'll be considering addressable memory. We'll be considering registers. There are three types of registers: general purpose registers. Remember, I told you that in the CPU are registers. Registers are like memory locations which are used to hold data during computation or execution. There are those described as general purpose. They are used for general purpose activities. And there are those that are identified as index and base. Index registers are the registers
But
that are useful for this for this subscription. Let me give you, well, you remember in programming, if you have an array and then you need to identify components of the arrays, subscripts comes very useful. So index registers are useful in addressing uh, or in implementing subscripts, or what we know as subscription in subscription in memory. Just a moment, somebody's trying to, wow. Okay. Now, base registers are also very useful in addressing the memory. We're going to see that much later. Then we have a set of registers that are known as specialized registers. They are necessary. They are used to they are dedicated to specialized activities. Then we also have some registers known as status flags. These registers present the current situation. The, these status registers uh, present the status of the current activities operating ongoing in the processor. And then we then have floating point registers. Floating point registers are specialized registers designed to hold floating points, decimal points. And then registers again that are dedicated to multimedia extensions. MMX means multimedia extensions, and also extended memories. So these are the categories of registers that are available in the 8086: general purpose, index and base registers, specialized registers, um, status um, flags, and floating points, multimedia extensions, and extended memory registers. Okay, so let's delve straight into this. Addressable memory. In a typical, in protected mode, because protected mode is able to recognize 32 bits, the total number of memory that can be addressed in the protected mode is 4 gigabytes. 2 raised to power 32 gives 4 gigabytes of information. That is, so in real address, because real address is limited to, I said 16-bit, but with the 4-bit addition, which makes it 20, is able to recognize 20 bits of memory space. 2 raised to power 20 gives 1 megabyte. So, as at 1991, 1992, the maximum memory space you can find on some very old computers known as XT, AT, maximum you can get is 1 megabyte of space. And then you can imagine how we managed to run computers then. I I I remember I wrote my final year project on a computer that was operating on maximum of 1 meg. That was 1994. No, 1995. It was a department for the department to parade set of computers that are 1 megabyte of that have 1 megabyte of space was how do I put it now, was a groundbreaking experience in the whole of the country. So computers then were operating uh, very, very crude monitors, maximum of 640 by maybe 480 resolution, 16 colors maximum. So these days now that you have resolution running into 1024 by maybe 1280, 16 million colors. You can imagine what you guys are enjoying. In those days, the best we could have was 640 by 480 resolution, 16 colors maximum. So um, that's about that. Now let's now look at the general purpose registers. General purpose general purpose registers. So this is the arrangement of the general purpose registers. Uh, the AX32 parade 32-bit general purpose registers. There are 8 of those, starting with the A, B, C, and D. General purpose. Sorry, yeah, general purpose, 8 of them. No, no, 4, 4. A, B, C, and D. The E simply means that extended. Typically, an AX register is 16 bits, but when it is extended, it becomes 32. A BX register is 16 bits. When it is extended, is 32. A CX register is 16 bits, and when it is extended, it extends to 32. Likewise, a D register is 16 bits. When it extends to 32. Now, let me just give you some shorthand. The A stands for accumulation, as accumulation simply means addition. So most times you find A registers used for arithmetic operations. B registers stand for base. The B registers will be used for base addressing, index, array, tables, and all of that. C stands for count. Whenever there's a need to do count, and we do counting during loop, when you need to loop and then you need the computer to monitor the loop. You want to do while, you want to do for loop, you want to so the C registers will be needed for the to manage the iterations. The D registers stands for D, so we use the D registers for data passing from one procedure to another. So now let's look at the base and the index on the other side. BP means base pointer. Base pointer, 16 bits, but when it is extended, it becomes 32. Stack pointer, SP. Stack pointer is a register that is used to monitor the stack. A stack is a specialized register in the it's a specialized memory which is used to manage data movement. Let me tell you what a stack can do. Do you know that on your computer, you are able to run several programs at the same time? You are in Microsoft Word, you are in Microsoft Excel, and you can switch in between the two. A stack is an infrastructure that ensures that whatever, when you switch from one application to another, information is not lost. And then wherever you left from, you are able to return to it. So that's very important. SI stands for source index. What does that mean? If you have two arrays, you are moving from array 1, array 2. Array 1 is your source, so you may use the source index to index the array, and then your destination, DI, destination index. Such a register will be needed for that. And when it is extended, it moves from 16 bits to 32 bits. Okay, let's move on. Now the flags, just the flag is can be 16-bit or 32. If it is E flag, then 32. Um, then you also have the instruction pointer. If it is extended instruction pointer, it is 32-bit. The instruction pointer holds the address of the next instruction to be fetched from memory. These are segment registers. Segment registers, there are 6 of those. CS stands for code register. That register contains the address of the segment that contains your code. SS stands for stack segment. It contains the address where your stack is defined in the memory. DS stands for data segment. Um, it can also be used as a code segment, meaning that that segment of memory that contains maybe your data or your code. Then the other 3, ES, FS, and GS, are extra in case you need to extend any of the 3 here, code, stack, or DS. You can use any of these 3 as extension. Okay, now I want us to look at how to access the structure of a typical register. I told you that a register that is defined as E, whether EA, EB, EC, ED, simply means 32 bits. And then if you remove the E, it only addresses the 16-bit, meaning that there are two 16 bits in 32. And then you can further split a 16-bit register into 2, each being 8. So let's start with this smallest. If you split a 16-bit register into 2, then it provides you two 8 bits. The lower 8-bit, that is from bit 7 to 0, is described as the low. For example, AL means the lower 8 bits of the A register, whereas the 8 to 15 bits describe the high order, the register, the A high order. So you can, in a typical 32-bit registers, you can split it into 4 different 8 bits. Now, how do you access it? You can only access one after the other. You are free to choose any of the sections. You can choose AL and use it separately from AH. You can use AX out of the EAX, and you can use the entire 32-bit EAX. So there are rules, and all of the same applies across from A to D. So likewise, the index and base register, 16 bits, 32 bits. I've mentioned all of those when I was describing. So I told you that AX accumulator, CX loop counter, SP stack pointer, SI, DI index register, source index, destination index. The BP simply means base pointer for stack. And then I've mentioned all of this code segment, data segment, stack segment, and additional segment. The EPI simply means instruction pointer, and then the E flags contains the status and control flags. Now let's look at the status flag. The status flag, as I told you, contain or present the status of operations that are currently ongoing. For example, if you have performed an arithmetic operation and there is a carry, for example, I say in base 2, 1 base 2 plus 1 base 2. If you do the addition, it's going to result to 0, 1. What does that mean? It's going to arrive at 0 with a carry of 1. So once that occurs, the carry that resulted from the operation is not implemented as a data, is implemented as a control, meaning that a flag will be raised to represent a carry. So that means that the next stage will then add the next stage will add to its operation the carry bit. Likewise, an overflow. An overflow simply means that there's a remember let's assume that you are performing operation on an 8-bit register. If you perform an arithmetic operation and it requires maybe 10 bits or 9 bits to represent it, it means there's an overflow. The bit that overflowed is not going to be trapped, but a flag is going to signal that, so that when next addition or arithmetic operation will be carried on, the processor will be reminded that there was an overflow in a previous operation. Another status flag is sign. If an operation resulted in negative -1 times +1, that operation should result in -1. -1 is represented as a signal, and then the sign bit is raised. If an operation results in a 0, then a 0 bit is raised. There's what is called an auxiliary carry. If there's a carry from bit 3 to bit 4, an auxiliary carry signal is raised. Parity, the number of 1 bit, if it is even or odd, depending on the setting, there is a signal to represent that. So all of these form status, or form the content of the status flag, which simply means describing the state of the activity that is currently being performed or that just currently being performed. Okay. Now, there are floating point registers. There are 8 of those. So 8 of those floating points, starting from ST0 to ST7, and each is 80 bits. There's a reason for that, and I will explain. 1/3 can be approximated to what? 0.33, but that's if you multiply it, it never gives you 1. The longer the significant figure, the higher the significant figure, the closer it is to the value. Because if you multiply 0.33 by 3, it never gives you 1. But the higher the resolution or the accuracy, the closer it is you get to 1, but you will never get to 1. So you can appreciate why each floating point register is 80 bits, just to ensure that um, the accuracy is high enough. And then they are arranged in a stack. What is a stack? A stack is a data structure. When you get to data structure, you'll be taught that a memory that has only one entry and one exit. What do I mean by that? You can you can make an entry and exit through the same door. It means that, and then you cannot perform the two operations at the same time. You must first exit before you can enter. Let's assume that you are interested in ST7. It means you must unstack ST0, ST1, ST2, ST3 up to ST6 to access ST7. And then when you are done, you will then restack. You start with ST6, 5, 4, 3, 2, 1, 0. So a stack is similar to a plate stack in your kitchen, where plates that arrive first goes to the bottom and plates that arrive last is on top. We describe that operation as first in, last out. If you arrive first, you'll be the last to get out. They are used for floating point arithmetics. Very, very key. Now, there are 8 64-bit multimedia extension registers. What are multimedia extension registers? Registers that are designed to handle audio, video data. These registers are designed such that multimedia operations can be performed seamlessly. For example, as I'm speaking, I'm also as I'm presenting this lecture, the audio signal is being transmitted and the visual signal is being transmitted. That's multimedia. There are specified registers, data that ensure that this operation is seamless, and each register is 64 bits each in size. And then there are 8 128-bit extended memory registers, which are used for multiple single instruction, multiple data operations. What do we mean by that? These kind of instructions allow for multiplexing. That is, on a single instruction, you can pack multiple data. This is to ensure that the processor is able to run several activities at the same time, because on one single instruction you can pack visual, audio data, please, at the same time, to ensure that the activities are run. So they're referred to as single instruction, multiple data operation. There are 8 of those, and each is 128 bits long. Okay, so we're done with memory management. So let's now move to 64-bit processor. No, sorry, we're done with processor architecture. Now we should move to memory. Does anybody have any question? Question, please. No question? You can type your question in the chat box or raise your electronic hand to ask your question.
Later. Okay, now.
Any question? Any question? Okay, so if there are no questions, let's move on. As I said, the class is being recorded. At the end of the class, I will share the video, the link to the video. So let's look at the instruction architecture 32 memory management. As I said earlier on, there is a real address mode. And we're going to look at how linear addresses are computed. We're also going to look at the protected mode. We're going to look at multi segment mode, and then paging. So let's start with the protected mode, which I mentioned earlier on to you. Okay. Now, protected mode provides 32 bits. So it means that 4 gigabytes of memory space is addressable. And what does that mean? If you look at my screen, you have it starts from 0 0 0 0 0 0 0 Each zero is 4 bits. So 4 times 8 gives 32, and it ends at FFF. Each F is 4 bits. So this is 4 gigabytes of memory space. Each program is assigned a memory partition which is protected from the other program. I mentioned to you, protected memory provides that there's a partition that is protected from other programs. So if a program consumes all of its memory, is unable to um, um, encroach into another program, into another memory partition. So it's protected. That's where the word protection comes in. And then the essence is designed for multitasking. So if memory location, if RAM, if the memory of a computer is partitioned into unique memory, it means that different activities can run in the memory. So so you can run several apps on your computer because the memory of your computer is partitioned, and each partition is protected from each other. So you're able to do multitasking. That is multiple program running at the same time on a single processor. And then pro operating systems such as Linux, um, Microsoft Windows support that, and likewise Android, iOS, almost all the languages operating systems now support um, multitasking, support protected mode. Now, okay, 64-bit processor. As I told you yesterday, 64-bit processor described the Pentium, a typical Pentium. It means that the operation is 64 bits. Uh, they have been designed to be compatible with older architecture, 16, 32, they're all supported. So that's why you can find on your Pentium architecture, for example, on your Pentium processor can support an operating system that is 32 bits or 64 bits. Um, so there is Windows 64 and there is Windows 32. Basic execution environment. Uh, address can be up to 64, but most time in most applications there are 48 bits. Um, there are 16 64-bit general purpose registers, and then the instruction pointer, just as I mentioned earlier on, EIP, which is 32 in this case, is described as is a 64-bit. And rather than being described, a 64-bit register being described as E, they are described as R. So an AX register that is 64-bit will be described as RAX. Remember, EAX describes 32-bit register, RAX is 64. So once letter R precedes the mnemonics or the symbol, then that gives an impression that should let you know that it's a 64-bit register. So can you see 34? These are 32 bits general purpose register, EAX, BX, all through, and then you have um, R9D, R910, all these are uh, 32-bit registers. Whereas the 64-bit register will be, for the A register will be RAX. So the B register will be RBX. The C register will be RCX. But when it gets here, this is R8. Remember, in 64-bit, there are 16 64-bit general purpose registers as against uh, 8 general purpose registers in 32. So, uh, R8, the 32-bit version is R8D. R9, the 32-bit version of that is R9D, and up to R15, and the 32-bit version is R15D. Okay, so component of an AI IA 32-bit microcomputer. So let's just look at the components: motherboard, video output, memory input output. So the motherboard is made up of CPU sockets, external. Let's look at the image. This is a typical 32-bit motherboard. It has memory slots. These are the memory slots. It has PCI slots for extension, peripheral connect, video output. These are defined audio chip, the firmware hub, the dynamic memory, power connector. So these are input output, mouse, keyboard, USB. So this is a typical motherboard, what it contains. The storage will be connected through here, ID, whether HDD or SSD rather. Then this is the chipset, the Intel chipset that drives the entire motherboard. And then you also have video outputs, provides a video controller, video memory, and then a port for um, the CRT, cathode ray tube on the display, and also make provision for LCD or modern display devices. So these are typical video controller for gaming or higher resolution video, maybe for video editing or for gaming. And then memory, different kinds of memory: ROM, EEPROM, dynamic memory, static memory, video RAM, CMOS. For the input output, USB, universal serial bus, quite intelligent, high speed, maximum speed 12 megabit per second, quite versatile. Parallel ports seem to have been discontinued. In those days, they were used for printers. Serial, well, serial too seems to have been upgraded to USB. You may not likely find this in computers these days. Device interface to connect devices for CD-ROM, um, other kinds of devices, Wi-Fi, Bluetooth. Yeah. So the levels of input in a typical in a typical in a typical device, there are three levels: BIOS, operating system. In a typical microcomputer, the BIOS. Once you start your computer, the BIOS means basic input output system. That's what comes up. And then if you are fast enough, you can break into the setup and check it opens up where you can make a connection. Drivers that communicate directly with the device are what you find here. Operating system security may prevent application level code from working at that level. Yes, high level security. Then that's the lowest level, level one. Level two is the operating system where APIs operate. And then level three is is the level at which um, high level languages such as Java, Python, uh, C, and a whole lot of other languages operate. Yep. Okay. Okay, so you can see here's a diagram to show the hardware is the lowest level, level zero. On top of that is the basic input output function. Built on that is the operating system function and then the application program. So this is the um, stack of the levels in a typical microcomputer. And in programming, an assembly language program can perform input output at each of the levels. You can use assembly to perform input output, that is, you can accept input or send input out at the hardware level. You can send it at the BIOS level. You can send it at the operating system level, and you can send it out. You can also operate at the library level. So, which makes assembly language very, very versatile. You can do inputs, outputs at the hardware level, level zero, BIOS level, operating system level, and at a library. You can write a library for it. So in summary, the whole of chapter 2 talked about CPU, ALU, instruction cycle, talked about multitasking, floating point units, complex instruction set, talked about the various memory mode, real and protected. We looked at the motherboard components, memory types, input, output, and access level. Um, thank you for your time. If you have questions, let's have questions. As I said, thank you so much for your reactions. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you so much. Now the lines are open. Let's have your comments, your question. Class rep, Treasure, can you unmute your microphone? Treasure.
Yes, sir, I can hear you, sir.
Okay, so you're gonna after this class, you and I will talk um, to find out how best how to integrate YouTube channel to this so that it would minimize the distraction having
Okay,
to admit and unadmit. So please let me have you so that we can see how best we can do this.
okay, sir. Thank you, sir.
Okay, so question. Let's have question and your comments. Okay, now uh, so the next class we're going to have maybe on Friday will be on practicals. I will introduce to you. Although we have a class on Thursday, that Thursday class we just go and discuss. I think Zoom is easier to connect. Yeah, Zoom is easier, but Zoom requires a paid uh, version. I don't have subscription to Zoom, so that's a challenge with Zoom. And without a paid version, we can only do 40 minutes. Zoom would have been excellent. You do have a question, yes? Ogechi, unmute your microphone and ask your question.
Okay, so my question is on those operation modes. Were they like the way you listed them out? Is that the way they were like made over time? Because you kept
Uh,
referring to the
let me go
first one,
back.
and I was wondering.
Let me go back to the operations mode. Well, the operations mode basically refer to the memory, yeah, the memory management. The very first mode is the real address, where the processor can address maximum of 640 megabytes with an extension to 1 megabyte. And then, and that is known to be as linear addresses. Shortly after that, we then had the protected mode, in which we can address up to 32 bits of memory location, and that gives us 4 gigabytes, in which the memory is partitioned into segments, and each segment is protected from each other. Although before we got into 32, we also had protected mode shortly after the real mode, in which we can do a maximum of maybe 2 megabytes, 4 megabytes. Those were around 1992, 93, when Windows recently brought up Windows 3.1, 3.2 with some challenges. But the real protected mode came in when we were able to do multiple segment model and paging. When you get to part 4, you're going to do micro, what's called operating system. You'll be taught more about this memory management, where different techniques have been brought in to assist the processor to manage its limited resource in terms of memory space. And then we had multiple segments, paging, and all of that. All of those allow the processor to partition its memory into chunks of um, contiguous spaces which are independent from one another. So to answer your question, yes, that's the sequence from real address 64 bits, very very restricted, very buggy, to the protected or the virtual mode that we have, that is 32 bit, which supports paging and all of the very very sophisticated memory management. Ogechi, did I answer your question?
Yes, sir. Thank you.
You're welcome. Yes. Any other question or comments? Okay, is it possible to interface assembly language with, let me check. Sorry, I'm managing. I'm trying to access your chat. I'm yet to locate your chat. Sorry. I have two of these to switch in between. Sorry, can you unmute your microphone and ask your question verbally? I I can't locate this chat.
Good evening, sir.
Good evening.
So I was trying to ask whether we could use assembly languages inside other high-level languages.
Oh, sure, sure, sure. In fact, that's one of the beauty. You know, I told you that in the class yesterday. I said assembly language has its beauty in its ability to interact with the operating system, to interact with the hardware. Even from this lecture, I told you, I said that the hardware assembly language is able to perform input output at all of the levels: hardware, BIOS, OS, and the library. And then the operations that are carried out at the hardware level are the most efficient. So you are able to, you are allowed to write routines. If you have any routine that requires efficiency in terms of speed, and then minimum at the minimum memory space, I would advise you to go for to implement that routine in assembly. You can do the others in high level language, but if you can identify a mission critical application, you are allowed to implement that as in assembly language, so that you can achieve that speed. Many that's Let me give you examples. I know in C programming language or C++, that happens a lot. You can write your code in C, but if you identify a particular activity that is mission critical, then you can go straight for assembly, and it's going to be a wow, because the application is going to come out superb. So it's a blend of usability or ease of programming, and then the power of computing. So yes, it's possible. Does that answer your question?
Yes, sir. Thank you.
Yeah. Any other question? Okay. In the absence of none, can we bring the class to a close? Okay, so thank you so much.